I think not quite 20 years ago, I was coming in here regularly, I think actually exactly at 3:10 on Wednesdays for advanced quantum physics. And you can tell by the fact that I'm now a groundwater modeler exactly how conducive to thought this room is at 3:10 p.m. on a Wednesday. So thank you for making it this far to this, the last of the concurrent sessions of this conference. So I'll be talking about the Goyder project that it's been my pleasure to lead. In fact, my continuing pleasure to lead. It doesn't actually finish until end of May, along with the 100 other also Goyder projects. And this one's on modelling salt dynamics in the River Murray floodplain in South Australia. Specifically, we are looking at the area between Morgan and the border because it's got specific kinds of dynamics which make it distinct from the downstream area. So that's the dark blue. Now I'd like to share this photo with you first. This is from a trip that we took, Jan Whittle, who's here in the audience, took us up to Chowla in December. And I think you have to agree, this is just a beautiful area. Luscious vegetation, looking really healthy. This is exactly what you want to see in a part of the River Murray floodplain. Whereas later in the day, we went to this site, which is exactly what you don't really want in the River Murray floodplain. A lot of dieback, just generally unhappy looking. And generally speaking, the major difference between those two sites is access to fresh water. There are complications, but that's the main one. And Todd, who is the second speaker, has a much clearer grasp of the ecological reasons. Why is salt a problem in the Murray floodplain in South Australia? Well, first up, it is just naturally extremely saline. It's highly unusual on the world, around the world. You get a tiny percentage of salt just in the rainfall, and in this semi-arid climate, and it's a almost closed groundwater basin, that means that when some of that water evaporates, the salt gets left behind. And over tens of thousands of years, that salt has become concentrated in the soil, and in particular in the groundwater. So throughout this area, the groundwater salinity is quite commonly half that of seawater and can be double. So really, you've got the River Murray flowing over and interacting with an aquifer system that's practically a sea. So that's the natural system, but as we tend to do, we've made the problem worse. River Murray flows, so the incoming fresh water have declined due to pulling out water for irrigation and latterly climate change. So we're seeing less fresh water in the channel, and we're seeing fewer floods and smaller floods. So less of that fresh water is getting into the wider parts of the floodplain. The other mechanism is that we're getting more salt into the floodplain. Irrigation sort of pushes saline groundwater into it. I have this nice little dynamic from Steve Barnett. So you introduce irrigation next to the river, close to your water source. That increases the drainage, raises the local water table, and that gradient means that more of the extremely saline groundwater is going into the river. So, salt, naturally an issue, but less fresh water into the floodplain, and but while we have more salt into the floodplain. On a more local scale, there can be other factors involved, grazing, cropping, and we significantly altered the balance between the river and the groundwater system when we introduced river locks. That's Pike, if anyone wants. Pike floodplain, that's the area we call the dead zone. So, salt management of the River Murray. Now, for almost at least 25 years now, we've had works to control river salinity that have included improving the efficiency of irrigation so we get less drainage, but also the development of engineering schemes such as the salt interception schemes to prevent some of that salt getting into the river. And increasingly, there are works to improve floodplain health. such as the environmental watering programs, which were talked about yesterday, regulator and whirlpool manipulation, and we're starting to look at whether or not how we can manipulate freshwater lenses within the groundwater next to the river. But because of all these things, we have an increasing need to understand conceptually how the dynamics of water and salt movement are in the floodplain, and from my point of view in particular, how to model that. A model, after all, is just your summary of your understanding of a particular site. If you put all that information in the model, it won't necessarily tell you what will happen in the future, but it will tell you whether, to the extent to which your understanding matches your observations. It's something you can improve on. So the state of modelling at the moment is that we have very, very nice models, if I say so myself, of the regional groundwater inputs, the salinity register mod flow models, which myself and a couple of other people in the room work on, Chris Lee and Katia Bushaway in particular. And our counterparts in surface water at JUNA have models, and at MDBA have models of the river. And now we're trying to navigate this mysterious zone in between them of floodplain models. And there have been quite a few really quite successful floodplain models, but they've all tended to use somewhat different techniques and assumptions, and we're trying to unravel which of those is best under what circumstances. Okay, so overall our project aim is to improve our understanding, conceptual knowledge, and the modelling capability of flow and salinity movement in the River Murray floodplain. And we anticipate that the results will assist with management and engineering decisions for those floodplains. The project team combines people from Flinders University, such as myself half of the time, including Tarek Latu, Adrian Werner. CSRO has been led by Kate Hollins and now by Peter Cook. And also we made sure to include quite a few people of JUNA, some of whom will be immediately using the work, and others included because we needed groundwater knowledge, surface water team knowledge, and policy knowledge, including Judith. So we have met before. Okay, so it's divided into two tasks. First one, data and literature review, fairly standard. And the main contributors to this were Tarek at Flinders and Dennis at CSRO, with some extra input from JUNA, from Chris and Katia. What we're trying to do, as well as just trying to gather together as much information as we could, what information was available on the floodplain, we were trying to take some of that data and analyse it in ways that it hadn't been looked at before. So in this case, this is summarising the outputs of 8 separate regional models and combining it all in a way that it's looking at how much salt is going into the river and ultimately how much salt is going into the floodplain, our best guess, okay, under different conditions for each river kilometre and each year, I think from 1920 to 2100. So this is a way of summarising our current best understanding and what the impacts of things such as the salt interception schemes have on that salt input to the floodplain. Another thing we're doing with the existing data is we're revisiting the salinity risks from depth to water, evapotranspiration being a very important part of the floodplain budget, get more salinity risk where the water table is close to the surface. So again, we've combined the outputs of those 8 existing models, which don't do a crash-hot job of simulating the floodplain, but they're still better than pretty much anything else we've got. Summarising that, subtracting off the ground surface LiDAR, and getting these maps of where we think we're going to have more of a salt problem. And we'll need to actually compare that with what we actually know about the salt problem and see if this is consistent. This might tell us more about the models, in fact, than the risk. We'll see. And we've also sourced some data sets which haven't been analysed before, such as fairly recently released satellite data on actual evapotranspiration from soil and groundwater. Dennis Gonzalez is currently doing quite a lot of work in analysing this data, So looking at how AET varies by location, by soil type, by vegetation type, and down the track we hope to be able to analyze it monthly and seasonally and see what's actually happening on the floodplain. But that's still going on. The other chunk of work that Tarek did was to review all of the past salinity risk assessments for the region, try and work out what had worked best in each of them, what sort of framework we could develop, and came up with some recommendations about how we might move forward to have a united framework across the area. But modelling is the focus. So we have quite a lot of options for how we could model the floodplain, surface water, groundwater interaction. Some of them are simpler than others. So your analytic, semi-analytic models, fast, simple, don't require very much data, probably not that accurate, except under peculiar circumstances. At the other end, you've got the very data-hungry, computationally intensive, simulate everything ever models. Hydrogeosphere is an example. And there would be a huge amount of work, actually. It should actually, and I do think it should be followed up, that we should investigate these different methods. But for the very time-constrained period that we have for this project, we decided to pick the two that are already currently being used by the department, by JUNA. So the source model, which is surface water focused, and ModFlow, which is groundwater focused. And CSRO is taking the lead on the source, and Flinders is taking the lead on the ModFlow modelling. So I've just got a couple of pages results from Peter Cook's initial analysis. What he's trying to look at is the flow from a wetland back to the River Murray. So you have a flood, the wetland fills up, the wetland, some of that will evaporate, and some of it will drain back, again pushing some salt into the river. So he had essentially some thought and programming experiments. How do you actually model that flow back to from the wetland? So let's see. That works. Good. So here's the river. Here's our draining wetland. What assumptions do we make? Do we assume that it's just going back at a constant velocity? That it's going back via multiple paths or one path at different velocities depending on the wetland? Is there evapotranspiration? Is there vegetation nearby? So he set up those simulations, and so here's your leakage times from the wetland, and my apologies, these do actually have different scales on the side, which makes it a little harder to interpret. But overall, what I want to convey is that what he's found is that your assumptions are critical. All of those could be quite reasonable conceptualizations of your wetland, depending on the site. But you get quite different changes in the timing of that salt back to the river, how it has moved through the floodplain, and in the amount that's appeared, and the frequency. So that leads to the next question of how do you say which kind of wetland is best modelled by which methodology? Do we have the data to support that? And it can lead to quite large changes in the overall cumulative salt flux from the wetland to the river, which is something we'd actually like to know. Meanwhile, Tarek and Virginia, with some input from Carl Purcell at JUNA, have been looking at the ModFlow model. They've set up a couple of different versions, one of which has a wide floodplain, which allows us to simulate the cases where the river is losing flow into the aquifer system, and also a case where you've got flow from groundwater into the river, and then on one side, and then from the river into the groundwater on the other side, the through-flow case. However, we quickly found that we couldn't simulate the other case, gaining stream, where we've got groundwater going into the river, couldn't simulate that in a wide floodplain, unless you had really severe groundwater gradients. So we also set up this second version where the river is quite close to the edge of the floodplain, so next to the cliff. And we also added a little wetland, so that's a dimple in rather than a dimple out. It does that sort of little flexing thing, optical illusion. Yep. so that we can compare our results with the source model. That's fairly standard boundary conditions. So the sorts of topics we're exploring include temporal discretization. How much detail do we need to put into that? Spatial discretization. What's the best way to simulate fluctuating river levels? Evapotranspiration, inundation. Our literature review showed that there were multiple ways of simulating these that all look quite reasonable. So we are currently comparing them all. Inundation, solute transport, so the mixing of fresh and saline waters, and freshwater lenses and density dependence. So very quickly, apparently. Here's one example. So this is us simulating changes in river level, and currently the models just have a flat river, incidentally. We're not even looking at this in the regional scale models, mostly speaking. So we compared annual approximations, annual averages, with monthly averages, with better than monthly averages, adaptive stress periods. What impact did that have? Well, for trying to simulate heads in the water table, monthly steps are good enough. Annual was terrible, monthly was fine, finer than that would give you a little bit more information, but not a lot. Whereas if you're interested in fluxes, and this really shouldn't be a surprise, but interested in fluxes, you really needed to have really quite a fine discretization of that river, much less than monthly steps, match that river level movement quite clearly. Otherwise, you would significantly underestimate the flux between the groundwater and the river system. How much time have I got? Okay. So I'll just briefly say we're doing something similar to evapotranspiration, and also looking at its sensitivity to the parameters we give, not varying it hugely, and spatially uniform versus spatially varying. And that just shows essentially that evapotranspiration is absolutely critical, both spatially and temporally, very sensitive to the parameters. In fact, it can change your river from gaining to losing with just a fairly small tweak. So understanding evapotranspiration is unfortunately very complicated, but very necessary. So what will come out from this project? We'll have recommendations for salinity risk approaches, recommendations for modelling, both in the rapid surface water focused source model and the more time-consuming detailed mod flow models. And we've got a huge laundry list of recommendations for further work, all the things that we'd really like to do and think are important, and hopefully a bit about how to apply that to floodplain management. Now, I'm actually pretty confident that this will be, the work that we're doing at Flinders will be used by JUNA because of these three projects, which we'll flow into. The SA Riverland Integrated Infrastructure Program, which is looking at how to better manage pike and cataractco. ARC linkage study on riverine freshwater lenses, with Flinders and Monash, and also further work on the salinity registers. I'm confident of that because I and my colleagues are also involved with all of those projects, so we will carefully hand over all our work to ourselves. No troubles too much coordinating with this project. So I think we're well on track to having an improved understanding of how water and salt move through those floodplains in a way that should be able to assist with management and engineering of those floodplains. Thank you.